All right, everyone. I think we're ready to get started. So thank you for coming out so early in the morning after a party. I appreciate it. This talk, I hope, will be interesting, or you can always fall asleep if you find it too boring. It's called 4 Languages from 40 Years Ago. I'm Scott Wlaschin. Also, what can we learn from the 1970s? The 1970s were a long time ago, and there's still some interesting things that we haven't really caught up with then. I have a website, fsharpfundandprofit.com, so I'm all about F-sharp, but I'm also interested in all sorts of other languages, and I will hope to explain why. So this is the 1970s. This is a photo taken back then. As you can see, it was a very ancient period. And amazingly, I am so old that I was actually alive in the 1970s. That's me down in the corner there. So yes, that's a family photo right here. So 40 years ago is a long time ago, but I think there's a lot of things we can learn from them. So I'm going to talk about 4, maybe 5 languages. I'm going to start with a brief history of programming languages, and then I'm going to talk about hammers and toolkits and why not everything is a hammer. And then I'm going to talk about my 4 languages and maybe my 5th language X from 1979, and you'll have to guess what that is. Okay, so let's start with a brief history. This is one of my favorite quotes. A language that doesn't affect the way you think about programming is not worth knowing. And as I talk about various languages, I'm going to give them the Galaxy Brain seal of approval. And that means that this language, if you learn this language, it will make your head explode. So that's good. Learning a language that doesn't make your head explode is a waste of time, basically. Right. So back in the 1950s, the pre-Cambrian era, there weren't even dinosaurs there. We had nothing but assembly languages. And then towards the end of the 50s, Fortran sort of crawled out of the water and made its appearance. And it was the first high-level language, and so it gets a Galaxy Brain because it completely changed the way people thought about programming. You didn't have to use per-machine assembly code. And then COBOL came out after that. That was the first enterprise language, as we all know. Lisp came out after that, and Lisp gets a Galaxy Brain just for existing because Lisp is the perfect language. We all know that Lisp is the perfect language, and has always been the perfect language forever and ever. And if you're interested in knowing why Lisp is not the dominant language today, you might read a very excellent essay called "Worse is Better." You find that on the internet. So, okay, in the 60s, it was all about IBM and the 7 Dwarves, which were the 7 other tiny companies compared to IBM. And the first important language of the 60s was ALGOL. And ALGOL was incredibly important language. It's basically the foundation of all modern imperative languages. So if you use C or Pascal or any of the modern languages, you can thank ALGOL for that. Very, very influential. BASIC came along. The idea for beginners, what a concept. PL1 came along. This is meant to be the kind of bastard child of Fortran and ALGOL, and it's meant to be the only language you'll ever need. So that's famous last words, of course, because people don't use PL1, except apparently you can actually get a .NET implementation of PL1 if you need it. So ISWIM, 1966. This is, it was never actually implemented. It was written up in a paper, but it's the most influential language that was never actually implemented. It's sort of like a Velvet Underground album. You know, nobody read the paper, but the people who did read the paper went away and created their own programming languages. It's the parent of all functional programming languages, and it's the first language to use indentation as scope. So if you use Python or Haskell or F-sharp, you can thank this language for that. APL, 1966. A long time ago. It's the first write-only language. It's famous for that. And actually, seriously, the point of the language was, the idea is you think in symbols. If you're a mathematician, you think in symbols, so you should write the code in symbols. And the notation was actually as an aid to thought. It was a very well thought-out language, and he actually got a Turing Award for inventing it. So it's actually, we shouldn't dump on APL. It's actually a very important language. So I'm going to give it a Galaxy Brain. If you learn APL, you're definitely going to have your mind blown. Simula 67, first language with classes and inheritance. Mads was talking about this in his keynote. So that also changed the way people thought about programming. It probably wouldn't blow your Galaxy brain today because you're used to this kind of stuff. But at the time, it was pretty impressive. BCPL is important because it's the first language with curly braces. So you can blame BCPL for everything else. And it's the grandparent of C. So that's a long time ago. It's 1967. That's 50 years ago, something like that. Logo. So Logo was amazing because the idea is you'd have a programming language for children to use. Now, this is when people still had mainframes. So the idea that you'd have young children programming a computer was really a pretty profound idea. Very, very insightful. Algol 68, the successor to Algol. Another influential language, very, very complex, never really took off, but was very influential. And that brings us to the 70s, which is the decade that I'm really going to be talking about. And in the 70s, a lot of things happened. Pretty much everything that we can think of as modern programming happened in the 1970s. So I call this the Cambrian explosion. Lots of new programming languages, lots of new programming paradigms. Starting with Forth. So Forth is the first concatenative language. That definitely blows your mind if you've ever used Forth. Galaxy brain for Forth. And there's a book called Thinking Forth, which I highly recommend reading. It's all about designing programs in a modular way, and that's where the word factoring, as in refactoring, came from. Pascal, 1970, that was really Algol, a nicer version of Algol for the rest of us. C came out in 1972. You've probably heard of that one. Still going strong. Prolog. So this is, I'm going to talk about Prolog. A new paradigm, logic programming, mind-blowing, okay? 1972, and it still hasn't really, most people aren't really aware of it. ML came out in 1973, another new paradigm, functional programming, another mind-blowing way of thinking about programming. SQL came out in 1974, another new paradigm, relational database programming. And that's mind-blowing. Again, completely different way of thinking about how you might interact with a computer that people hadn't really ever thought about before. CLU is worth a mention. They introduced abstract data types and so on, very influential, written by Barbara Liskov and her team. And so if you've heard of the Liskov substitution principle, that is named after her. Scheme came out. That's another Lisp for the rest of us, people who don't like Common Lisp like Scheme. Microsoft Basic came out. And that was amazing because you could actually program a personal computer. Like the original Altair, you had to flip little switches, and with BASIC, you could actually do some little programming, which is amazing. Smalltalk came out, and that's another mind-blowing language. Along with Lisp and Smalltalk are basically the two most influential languages, I would say. All sorts of stuff came out of Smalltalk, and I will be spending a lot of time on Smalltalk. A lot of people say it's a real OO language, not like Simula. Not like Java and so on. We will see. I will talk about OO in a minute. The other interesting thing about Smalltalk is that the ex-practitioners of Smalltalk are very, very influential. The Gang of Four Patents book had Smalltalk as one of the languages. Kent Beck from XP was an ex-Smalltalker. A lot of the Agile people were ex-Smalltalkers. Martin Fowler of refactoring fame was an ex-Smalltalker. So they really have infiltrated the modern world of programming. Module 2, I'm just going to give this an honorable mention. It's sort of a Golang of the 1970s. It had a great module system. It had coroutines. It had all sorts of cool stuff, but never really took off, unfortunately. But it was a very cool language. Still a pretty cool language today. And it was designed for doing operating systems, not just high-level stuff. And language X from November 79, I think just squeaks under the wire. And I'm not really going to tell you what it is, except that it's the grandparent of the most popular programming language ever. So that gives you a clue, and you can think about what that is. And that definitely changed the way people thought about programming too. Right, so if you look at the most important programming paradigms, you have the imperative thing, really implemented by Algol and not really changed much since. Object-oriented, similar, and Smalltalk. Functional programming started with ML, symbolic programming started with Lisp, but really kind of took off in the 70s with MacLisp and Scheme and so on. Logic programming, Prolog in the 1970s, stack-based programming, Forth in the 1970s. What's interesting is all these paradigms really solidified by the late 70s and early 80s. And these are the paradigms we still use today. And we really haven't progressed that much. I mean, there are some new things in in programming technology. There's things like pure functional programming like Haskell, and there's Erlang and so on. But, most of us don't even understand this set of paradigms, let alone, So I would just encourage people to catch up with the 1980s, okay? Catch up with the 1980s state-of-the-art programming. That would be a fantastically useful thing just right there. So here's a toolkit. If you do some craftsmanship around the house, you obviously have a hammer for hammering nails. For screwing things in, you probably use a hammer. For cutting wood, you probably want to use a hammer for that, and for tightening bolts, you want to use a hammer, right? Is that true? No, of course it's not true. So think about programming, okay? You have lots of different things you do when you do programming. You do domain modeling, and you maybe use a hammer. And then to implement complex business rules, maybe you want to use a hammer. And for doing complex data queries, you want to use a hammer. And for doing live coding and stuff, you want to use a hammer. No. Exactly the same thing applies. You should be using the right tool for the job. And many of us only know one tool. We only have hammers. And in this talk, I really want to encourage you to go out and figure out how to use a screwdriver and a saw and a wrench, So if you look at the most popular programming languages, right, these are all the ones that you've all heard of. They're all basically the same language. And this is... you think, well, they're slightly different. They're subtly different, but you don't get a galaxy brain for learning Java if you know C# or Go or Visual Basic. They're really all the same language. I mean, it's like if I said, I speak 3 languages, I'm a real polyglot. I speak British English, and I speak American English, and I speak Australian English. No, I don't speak 3 languages. I mean, yeah, they're slightly different. They're dialects, but you don't get a galaxy brain for speaking 3 dialects of English, If you really want to make your head hurt, go and learn an African language or an Asian language or a Native American language. They will make your head explode. Learning different dialects of British is not going to make your head explode. So it's a big world out there. Please go and explore it. Not every language has to look like C, C#, Java, and JavaScript. Right, so let's go exploring. Let's start with our first language, which is SQL. Now, most people are very familiar with SQL. It seems really boring. But I think there's some cool things that we can get from SQL if we look at it with some fresh eyes, So first of all, it is actually originally pronounced SQL, not SQL. And it was part of the first relational database. So it was sort of a proof of concept for relational database systems. And before you had SQL, you had a dark ages where everyone had a proprietary API, and all the databases had different ways of talking to them, and you had to use different things each time. Very complicated, and SQL really got rid of this. I mean, the idea of, having different database APIs, was crazy. And sadly, we're sort of kind of going back to that a little bit, but, SQL is a fantastic step forward. So what can we learn from SQL? Well, the first thing is it's got a consistent model. Everything is relations. So we've got tables, which is a set of rows. Here's some people with ages, and here's some parent-child relationships. Everything is a relation. Everything is a row, a set of rows. So when you do something like select a name from a table, that's a projection. And that gives you back another set. Or if you do a filter and you filter by age, that gives you back another set. So no matter what you do, whether you do a projection or you do a filter, whatever, you're always getting another set of rows. So it's an absolutely consistent model. And what's cool about a consistent model is it's predictable. So, for example, if you tell me that this system uses set-based operations, and it's like, oh yeah, you can do this kind of thing, you can do this kind of thing, and I say, well, that's interesting. Since it's a set-based thing, I bet they can do Cartesian products, right? And then you say, yeah, here you go, join. So even without knowing anything about SQL, the fact that they can, the fact that it's a set-based thing, chances are they have something to do Cartesian products because it's predictable. I would predict just the fact they have a consistent model that they will do that. So anytime you don't have consistency, it makes it really hard to predict what's going on. So if you ever design the system, try and make the system consistent, and it makes it easier for the people who are going to use it. Now another thing about SQL, which is not necessarily obvious to people, is it's an expression-based language. So what do I mean by an expression? What I mean is that everything you do returns something. So when you do a query like this, it returns a set, right? Now because it returns something, you can embed it as a subquery in a bigger one. And you can take this query and embed it in a bigger subquery. So because it returns things, expression-based languages are composable, kind of like Lego. You can take two pieces of Lego and glue them to make a bigger piece of Lego. You can take two SQL statements and glue them together to make a bigger SQL expression. So expressions are great. Expression-based languages, you can do this. In a statement-based language like C# and Java, you can't do this. They're not composable. There's another reason why expressions are really nice, and that is because they don't have as many problems, not as many potential bugs as statement-based languages. So I'm going to switch to kind of a C-like language to demonstrate. Here's some C-like code. What kinds of things can go wrong with this? Okay, so we have a result variable, and the thing is it's initialized before it's actually assigned to. So we have to decide what are we going to initialize it to, or maybe we forget to initialize it. You know, that's a problem. And what about if we forget to assign it in the middle of the if statement? So one of the branches, now obviously it's pretty clear here, but if you have a very long branch, a lot of ifs and stuff, it's quite easy to forget to assign to it. And that can cause a bug. In fact, it probably has caused important bugs. And then what happens if there's an else branch? You haven't even thought about that, right? What happens to the value of result on the else case? And then finally, because result is outside the if statement, it's a side effect, and you can't take this if statement and refactor it. You can't pull it out as an extract method. So that's a problem. Now, if you write the same thing using the ternary operator, which C has, it's one of the few kind of expression things that C languages have, the result variable is assigned after. I don't have to kind of declare it first and assign it after. It's assigned and declared at the same time. And so I never have to worry about what is the default, what is the initial value when I haven't assigned it, because it can't happen. Similarly, I can't forget to assign it because all the branches return something, and I just assign the whole thing to the return value. And in a ternary expression, you have to have an else case. You can't say, well, if it's true, do this, but if it's false, I don't know. You always have to handle both cases. So you're never going to forget something. And because there's no side effects in that little ternary expression, I can take that ternary expression and literally refactor it. I can pull it out into its own little sub-expression like that. Now, obviously, this is a super trivial case, but in expression-based languages, which most functional languages are, and SQL is, this kind of refactoring, this kind of not having to worry about things that can go wrong is really natural. And it's a shame that it's not more common in other languages. So expressions are great because they reduce bugs and they make refactoring easier. So another tick for that. Another important thing about SQL, as a sort of design lesson, is it's declarative. You don't tell SQL how to do something, you tell it what you want to do. So let's say I want to find all the people older than 50 or whatever. Now, if you do the how programming, you're going to have to open a file, read through all the rows, you try to find a thing. There's a lot of stuff, that buries what you're actually trying to do. Now, if you look at the SQL equivalent, you just say, select people where the age is greater than 50. I don't care whether you have to open a file to do that. I don't really know. I don't want to know how you do it behind the scenes. I just want to know what I want to do. I'm telling you what I want to do. And one bonus about this approach is that performance is independent of the query. So if this is a slow query, I can just add an index. I can tune it without having to rewrite my code. If I go back to the C kind of code, and I say, well, this is slow, if I want to tune it, I have to rewrite this code. So I have to start, maybe inline the loops or do stuff. I have to change what I do in order to get performance. So my code has to change, which is a chance for it to break. With SQL, it's orthogonal. What you want to do and how you do it are completely separate. That's a really good design lesson if you're ever designing APIs. Make sure you focus on the what and not the how. And finally, SQL has separation of concerns. We're always told don't mix different things together. SQL is a great example of that because it's a query language, right? So it has select and it has where, right? Now, if you want to do an insert or an update, that's a different language. That's the data manipulation language. And they're different languages. I mean, they look like they're all in one pile, but they're actually, different languages. They're defined differently. And then if you want to define tables and stuff, that's yet another language. Now, we do think of SQL meaning all these things together, but technically they are different things. And the first one, the data query language, is the one that's an expression-based language. So keep your concerns separate. Don't try and mix them up. It makes implementation easy, and you can get a lot of benefits from doing that. Okay, so Be predictable. If you're ever designing, a lot of these things, obviously you're not designing a programming language, but if you're designing an API, you're designing interfaces, you're designing just the concept of a system, these are good guidelines. Be predictable, use a consistent model. If you are using a language, try and use an expression-based language. It makes your code more composable. And if you're exposing an API, focus on exposing the what and not the how. And in all your coding, please try and separate your concerns. Don't mix, different things together. And finally, SQL is an interactive language. You don't, when you run a SQL query, you don't compile it and wait 10 minutes and then see what happens, right? You can try things out. You can play. You can experiment. That's really, really important. That makes the language much more attractive to people. So interactivity is something we really, as humans, we love to play with things. So interactivity is really, really important. So this is all the stuff we can learn from a boring language like SQL. Okay, so who thought that SQL would be so interesting? Well, there you go. And especially the expression-based stuff. It's really sad that, in the 1970s, we had this figured out, and even today, most popular languages are not expression-based. And most popular languages do not separate concerns. And most popular languages do not have a declarative interface and so on. And a lot of them are kitchen sink languages. They don't have a predictable model. It's kind of sad that we really haven't progressed that much since the 70s. All right. Now for the first sort of mind-blowing one for people who are not familiar with this. So Prolog was the first mainstream logic programming language. It's designed in France, and it stands for Programming in Logic. And it was very big in Europe during the days when AI was very big in the 70s. It was the European answer to Lisp, and it was also big in Japan, just like most pop stars. So what can we learn from Prolog? Well, again, Prolog has a very, very consistent model. Everything is a fact or a rule, and that's pretty much it. So what do I mean by a fact? So here's some facts. Liz is 92, Charles is 69, and so on. And Charles is the parent of Wills, and Liz is the parent of Charles, and so on. Those are facts. They're just like a SQL table with relationships between the tables. Now, unlike SQL, Prolog has rules which makes relationships. So you can say a person is older than a particular age if the person has an age and that age is greater than the age you pass in. And one person is older than another person if the first person has an age, the second person has an age, and the first age is bigger than the second age. So those are kinds of rules. Now within Prolog, that's part of the database. The rules are part of the database. Unlike SQL, where you'd have to write a separate kind of stored proc or something, this is actually part of the database. So Prolog can exploit this. And again, Prolog is a declarative thing. When I want to do a query, I say, I can just say, what is the age of Liz? And if it's 92, that's true. And if I say, which person has age 92, it will basically go through the list of facts and try and find someone who has that age. And then it will, since I've got this variable p, which is kind of unbound, it's a kind of free variable, it will say, oh, p must be Liz. And it will return that. And if I do it backwards, if I say, what is the age of Liz, and I leave the age variable kind of unbound, it will go through the list of facts, and it'll say, well, this fact matches. I'm going to assign A has to be 92. So it's not a query, it's what they call unification. It's like you've got one thing over here, you've got another thing over here, they must be the same, so I will make this thing be the same as this other thing over here, unifying the two. And what's cool is it works in both directions, and we'll see an example of that. So it's a bi-directional kind of, you don't have to have queries for this thing and a different kind of query for this thing. It's the same model all the way through. Here's another example. Is Liz the grandparent of Harry? Yes, because it uses the rule that I had. If someone's a parent and they're the parent's parent. Here's another one. If the P is unbound, it will figure out who the grandparent is. So this is an example of it's using the list of facts, but it's also using the rule that I said, that a grandparent is the parent of a parent. And so on and so forth. Okay, so a lot of people would say, this is kind of cool. This is kind of like SQL. I could do kind of query language like this. And the answer is yes. In fact, there is a query language based on Prolog, and it's called Datalog. And let me give you an example. So here's a kind of really complex query. Get me the names and addresses of employees who work for at least one project located in Houston, but whose department does not have a location in Houston. Now, you basically set up a rule, say that if a manager works on a project and the project is based in Houston, then that's one thing. And then if a manager has a department and the department is not in Houston, that's another thing. And then finally, you say, well, get me the first, middle, last, and address of an employee who has a manager, and the manager works on this project, and the manager's not in Houston. So this is actually a database query, and it looks very much like Prolog. You're basically filling in various slots. So you don't have to write any joins. I mean, if you try to write this in SQL, there'd be a lot of really complicated joins going on behind the scenes, and you wouldn't really be sure that you got it right either. With the Prolog style, you just fill in the slots of the things, and then you say, well, this manager over here has to be the same as this manager over here, and that unifies them together, and therefore the two things are the same. So that's kind of cool. All right, let's look at bidirectional unification. So Prolog has a function called append, which takes a list and another list and makes a new list. So if I say, what if you take the list 1 and you take the list of 2 and 3 and you append them, what do you get? Well, you get 1, 2, 3. Okay, so that's kind of like a regular function. But what's cool is you can put it backwards. You can say, I don't know what x is. If I said that x is something and you append 2 and 3 to it, you get the list 1, 2, 3. What is x? And it says, well, x must be 1. So it will work backwards. The same thing. It will actually work backwards and tell you what you need to do to make this thing happen. Or you can be even cleverer and you can say, well, I have two things, x and y, and when I concatenate them, I want to make a new list, 1, 2, 3. What are x and y? Well, Prolog will say, well, x could be an empty list, and y could be the list 1, 2, 3. That would work. And then it will go to the next thing and say, well, you could also have x be the list 1, and y could be 2 and 3, or x could be 1 and 2, and y could be 3, or x could be 1, 2, and 3. Prolog will actually find all the different solutions. So this same function can be used in 3 different ways. It can be used to like find the answer to something. How do I append 2 lists? But it can also be find what do I have to do in order to get this particular result. So it's kind of backtracking. It's goal seeking. So if you ever used something like in Excel where they have a kind of goal scenario thing, it's exactly that. It's like, what do I have to make this to match this thing over here? That's really, really an awesome feature. So let me quickly demo Prolog here. So this is, here's my little database here. And I can say, here we go. Who is the grandparent of Liz? And the answer is Wills. And if I say, is Wills the grandparent, that's true. Whoops, I need to put a thing. Sorry, I'm typing badly here. And then I say, who is the grandparent of Wills, say? And it will say Liz. So it works in all sorts of directions. Now, obviously that's a trivial example, but a great example of how you can do this is something like Sudoku. So Sudoku is a good example of constraint-based programming. You have a system, there's certain rules you have to follow, and you're trying to find something that matches all the rules. You want to find the best answer. And this is, obviously Sudoku is a game, but in a lot of business situations you have exactly this thing. You want to find, given this constraint and this constraint, what is the best price that I should give? If I have this special offer and this special offer, what should I set the price to be? Really kind of complicated logic. Now, this is Sudoku in Prolog in 8 lines of code. Okay. So, and you don't tell it how to solve the problem. You say, what is the problem? You say, okay, there's an array of rows, and there's 9 of them. And then each row has the same length, and it also has to be 9. And then each row has a set of values, and the values have to be in the set 1 to 9. And then each row, all the values in each row have to be distinct. And then if you transpose the rows, you get a set of columns. And all the numbers in the columns have to be distinct. And the final thing is the little squares, the 9 little blocks. So we're going to give them names. We're going to say row is A, B, C, D, E, and we're going to say that the blocks in the first 3 rows, A, B, C, have to be different, and the blocks in the second 3 rows have to be different, and the blocks in the third rows have to be different. And that is it. So I haven't told Prolog how to solve the problem. I've just set up what the rules are for the game. And then if I go over here, and I say, can you solve this problem, Prolog? And there it is, it solved it. So it's basically applied all those rules and solved Sudoku for us. So, and that's really, really cool. You know, trying to imagine writing a Sudoku solver in another language is painful, and you're never going to be sure you got it right. All you have to do in Prolog is write down the definition of what Sudoku is, and it will figure out the rest. And if you have a bad situation, like here in the second one, I've got 2 8s in the same row. Okay, so that's not possible. That's going to be a bad answer. So I go to Prolog and I say, can you solve problem 2? And it says false. Okay, there is no solution to that because it's constraint-based. So I think, you know, this is an example. Obviously, Sudoku is you know, a trivial example, but people use Prolog for things like medical databases, for natural language processing, for all sorts of business rules. If you have these kinds of problems, any kind of constraint-based solving, Prolog is awesome for that. So what can we learn about Prolog? Well, again, it's consistent. There's only one way of doing things in Prolog. You either have facts and rules. You know, you have a completely predictable. You don't have special edge cases. You don't have weird little kitchen sink things. It's very, very straightforward. Again, it's very declarative. You don't tell Prolog what to do. You set up the rules and it figures it out, which is really, really a great way of solving problems. Unification is really awesome. The fact that you can do bidirectional queries, you can ask, you know, is this problem solvable? And, you know, is the Sudoku problem solvable? I could ask, is it true or false? And also, if I have some left things blank, I can say, well, which things match these slots in order to make everything work again. And again, it's interactive. I can play with it interactively. I can experiment. So if you ever write a rules engine, don't. If you ever do any complex business rules, you know, consider using Prolog. You can slot it in. It's got an API. You can call it from other languages. Definitely worth checking out. All right, and now next one, ML. So ML stands for meta language, written in 1973 or so, or started. All these dates are very fuzzy. You know, they kind of start writing it, and then it doesn't really, it takes a while to become stable. So I don't think it was really stable until the end of the 70s. But designed as part of the theorem proving system, so it's got this kind of logic thing again. Not to be confused with machine learning, obviously. It's an impure functional language, pretty much the first mainstream functional language, and it's the parent of a whole branch of functional languages, including standard ML, OCaml, and F#. There's another branch represented by Haskell, which comes from Miranda, which is a slightly different kind of history there. All right, now ML is a functional programming language. I'm not going to talk about functional programming because we've already talked enough about functional programming. So I'm going to talk about other things that ML can teach us, which has nothing to do with functional programming. So the first thing that ML had, which is really cool, is type inference. So let me explain how type inference works for people who aren't familiar with it. And type inference uses pretty much the same algorithm as Prolog's unification. It's like I have this thing has to be an int, and I don't know what this thing is, therefore this thing has to be an int. So it's kind of making them be the same thing. So let's look at an example. Here's a function, does something, I don't care what. There are two parameters, f and x, and I haven't told you what type they are. I haven't put any types in there whatsoever. So can the type inference thing figure out what those types are without me saying what they are? Well, the answer is yes, it can. And the first thing it does is it says, well, x must be an int. Because you're adding it to 1, and 1's an int, x must also be an int. Okay? And then it says the same thing. If you're adding y to hello, then y must be a string. So now we know that x is an int and y is a string. And then we look at this function, and the input to this function is now an integer. We know that because it's x. And the output of this function is y, so it must be a string. So this function must be something that turns integers into strings. So now we know what that function is. And now we know everything about the type. We can say there's a function parameter, which is an int string function. The x parameter is going to be an integer. And the final return value is going to be hello plus y, and we know that's a string. So the type inference algorithm has figured all this stuff out. without us having to tell it. And so this code up there kind of looks like a scripting language. It looks like Python or Ruby or something, but it's actually statically typed. You don't have to, you get all the benefits of type checking without all the overhead of having to tell the compiler all the time. Now you think, well, this is a trivial little example. Why is it really important? Here's a more complex version. This is C# for the link method called group by. Now I challenge you to understand what is going on. You have an enumerable which contains a grouping, which contains a T key and a T source and so on. Could you write this type signature yourself? Right? I mean, maybe some people could, but it's complicated. Now in F#, the same code looks like this. You group by, you have a source and you have a key selector. Now the F# compiler will do type inference and it will figure all this stuff out for you. So, you don't have to try and figure this stuff out. So the thing about type inference is obviously it's less typing. You don't have to type all the words in. But more importantly, there's less noise. There's more focus on logic and less focus on kind of fluff. All this type stuff kind of gets in the way. I don't really care what the types are. I just want it to work. The type checker will make sure that I don't make a mistake. Okay, another important thing about ML, which is kind of a little minor thing, but I think it's actually not so minor, different defaults. So in ML-based languages, things are immutable by default. And if you want mutability, that's a special case. Now that's the completely opposite of most kind of C-like languages where mutability is the default. And if you want immutability, you have to do a lot of extra work. Things are non-null by default. And if you want nullability, that's a special case. And that's, again, the exact opposite of most C-like languages. You get structural equality by default. If you have two data structures, they're going to be equal by default if they have the same values. So all that time you've written, overriding equals and overriding hash code and stuff, you don't have to do that. If you want reference equality, you can do that, and that's a special case. And all the data structures have to be initialized. You can never have uninitialized values. That's the default. Again, so you never have accidentally null, you never have accidental things that you forgot to handle. So even these simple defaults actually can make a really, really big difference in how useful the programming language is. All right, number 3, algebraic type system. And as I prefer to call it, a composable type system. And if you went to my talk earlier on the power of composition, this is the same little bit I'm going to repeat here. So what do I mean by a composable type system? In ML languages, the types don't have behavior. It's a functional language, so there's no behavior with the types. It's just data. So the good thing about that is because they're just data, you can glue them together because you don't have to worry about what the behavior is. And you can glue them together in 2 different ways. You can AND them together and you can OR them together. And what do I mean by that? Okay, well, ANDing is something we're all familiar with. If I say I want a fruit salad, it's an apple and a banana and a cherry. That is basically a record type or a pair or a tuple, things you're very familiar with. In F# it looks like this. This is very similar to how you do it in C# or JavaScript or something. It's just basically a record structure and that we're all familiar with. So nothing special there. But the other thing which ML languages have is composing with OR. So if I say a snack is an apple or a banana or a cherry, this is the kind of thing that's not so easily available in most modern languages. In F# you'd write like this. You say it's an apple or a banana or a cherry. Now it's sort of like an enum, sort of like subclassing, sort of, not really. It's a different concept, and it's a really fantastic concept, and we'll see in a minute. These are called, I like to call them choice types, because it's a choice of different things. They're called discriminated unions. They're also called sum types. Lots of different words for these things, but really, really a valuable thing. Once you have this thing in your toolkit, it's really hard to go to a language which doesn't have it. So let's look at a real-world example. Let's say that we have 3 forms of payment we want to take: cash, check, and cards. And for checks, we need extra information, and for cards, we need some extra information. So how would you implement this? Well, in an OO way, you might have an interface and subclasses and so on. In an algebraic type system, you build up the model using types by building smaller types and bigger types. I mean, building bigger types and smaller types, just like Lego. So you start off with some small primitive types like this, check number and a card number. Okay, they're primitives. And then you say, okay, a card type is a choice between Visa and MasterCard. And credit card information is an and. It's a card type and a card number. Okay, so it's a record structure. So we've got a choice using or, and we've got a record using and. Okay, now we've built up some more types. Let's use those. We can say, okay, a payment method is a choice. It's either cash or check. And if it is a check, we have the check number. Or it's a card. And if it's a card, we have some extra card information. That's a choice type. And then we can build on that. And we can say, okay, we need a payment amount. That's a decimal. A currency, that's a choice. So another primitive, another choice. And then we can build on that. And we can say a payment is an amount, and it's a currency, and it's a method. So we've actually built quite a big domain in a few lines of code, right? That's the final one's a record type. This thing of building bigger types and small types is really, really powerful concept. And this is one of the really nice things about algebraic type system. And if you do this, you get this kind of thing as types as documentation. Something we're always trying to go for, right? Types as executable documentation. So this is a bunch of types. And I think you can understand, what this is about. This is nothing to do with playing cards. This is a card game, right? Just from the way the types look, you can guess what it does. And types can be nouns, but they can also be verbs. You can have function types. Say, this is how you deal. This is how you pick up a card. So you've basically got the entire domain on one screen. You don't have to go to 20 different files, to 20 different classes to try and figure out what the domain is. In a functional language, you typically have this as the first file in your program, and all the rest of the stuff uses this as the basis of its implementation. And what's nice about this is that even a non-technical developer can look at this code and understand it. So if I show this to a non-technical person, I say, what payment methods are accepted? They don't have to be a programmer. They can probably look at this and tell me. And if they say, well, you forgot to handle PayPal or something, they can look at this and give me some feedback. And that's really nice. If you're doing domain-driven design or something like this, where you're working with domain experts, this is a fantastic way of doing this. So obviously a massive topic. I have a whole talk about this, and I have a whole book about this. So if you want more about this, go and read my book. All right. I'm not going to do a demo of ML, because there's been a lot of F# demos at this conference. I highly recommend Thomas Petracek's demo of how to build Excel in an hour. And there's a lot of other good talks at this conference that you can see. Right, what can we learn from ML? It's expression-based again. Everything is composable. You can take ML expressions and build bigger expressions from smaller ones. This composability thing, harp on over and over again. We've got composable expressions, we've got composable types. Building bigger things from small things like Lego is a really, really powerful principle. Type inference is absolutely awesome, and any language that doesn't have type inference is a loser. Seriously. Just making the defaults different. Again, this applies, obviously you're not writing programming languages, but if you're ever designing anything, think about what the defaults are. Make sure the defaults make it hard to do bad things. So make sure the defaults, always work. So for example, having a mutability by default is really helpful. If you want mutability, fine, you can ask for it, but it's not the default thing. Make the default thing the good thing. ML was the first language to introduce parametric polymorphism, which we call generics, and incredibly, even in the current era, we have some languages which do not have generics, mentioning no names. Algebraic types are awesome. Going back to type inference, Java developers just got var, right? Very, very simple type inference, and people are freaking out over it. Like, dude, this has been around for 40 years, okay? And algebraic types have been around for 40 years, and people don't even have them in most languages. It's like, what are we even doing? Right, and now Smalltalk. So, I heart Smalltalk. I love Smalltalk. It was my first love, as it were, and I still love Smalltalk very much. Developed at Xerox PARC, where they did everything. They invented the PC, the first GUI, the first laser printer, they invented the Ethernet. They did everything there, pretty amazing. And when they introduced Smalltalk, it was the first message-based OO. They introduced Model View Controller. They had a full IDE on a graphical user interface back in the 1970s. It had a virtual machine. It had a generational Java collector. Really incredible. So Galaxy Brain, many, many Galaxy Brains to Smalltalk for being awesome. This is what the Smalltalk user interface looked like back in the 80s. Back in the 80s with the Mac. And it really hasn't changed since then. And you'll see in a minute that it's pretty much the same interface. So I'm going to do a Smalltalk demo because I can't really, there's no point even showing you the code. But Smalltalk has a consistent model like all the other ones we talked about. Everything's an object. Everything's an object. Everything is an object. I cannot stress this highly enough. Everything is an object. It's got minimal syntax. It has 3 keywords, and it has 3 kinds of messages, and that is it. So everything is done through the language. So, for example, there's no if statements, and there's no for loops in Smalltalk. Everything is done through messages. Now, a good example, a modern example of this is how async was done in C# versus F#. So in C#, they just added async a while ago, and they had to add a new keyword for async. They had to change the language to do async. In F# has a facility for doing things like that, and they could just add it as a library. The language is already powerful enough to add async as a sort of library. And that's one of the differences between making a powerful language and a language where you have to keep changing the syntax all the time. The other thing about Smalltalk, which people aren't really used to either, which is the whole concept of late binding. So late binding means that you don't really do anything till the very, very last minute, and you can intercept a message at any point up to the last point and work with it, change it, route it. So if you're going to be a dynamic language like Python or Ruby, be a really dynamic language. I mean, really go whole hog and be as dynamic as you possibly can. And Smalltalk is really the ultimate dynamic language. And another interesting thing about Smalltalk, no text files. Everything is in memory all the time, and which means that everything's already there. Every single file, every single class, every single object is always in memory all the time. And you might think, well, that's a lot of memory. It's like, no, it's a lot less memory than a tab in Chrome. You know, it's tiny. 2 megabytes, maybe. I mean, I worked on a Smalltalk image that was 2 megabytes back in the 80s, you know, and it hasn't changed that much. So let's do a Smalltalk demo. And here we go. Right, so here is an integer, 42, and make it a bit bigger. And you can send it messages like hex. What is your hex? Well, it's 2A. And then I can say, you know, add yourself to a float, 2.2. And it prints out 45. So you can see that it's all very interactive. The answers actually show on the screen right next to this, so I can actually use the answers. So it prints the answers right next to what you're doing. So this is what you call a keyword message, where you have a parameter. Something like hex is a unary message with no parameters, and then of course you can have binary messages. And that is it. That's the entire Smalltalk message passing system. Smalltalk is kind of cool. There's no surprises in Smalltalk. If I say, what is 1/2? Smalltalk says it's a half. If I say, what is 1/2 plus 1/3? It says 5/6. Okay, so fractions are built in. The idea is you don't have to know about floating point, and you don't have to know about what the max int is. I mean, here's another good example. If I say 42 factorial, am I going to get an overflow? No, I'm going to get a very large number back. So, you know, it doesn't. The whole point, it hides. It's an interface. Why should you know? Why should you care what the max int is? You know, it's not relevant to your programming. You focus on what the goal is. So everything is an object. Now, if I want to do this late binding thing, if I say hello to 42, it will say small integer does not understand hello. Right? Now I could say, okay, maybe I made a mistake. Well, maybe I do want to make, you know. So what I go is I go into the debugger, and rather than saying, oh, I made a mistake, I'm just going to define a new method right now. Hello. Okay, and I've saved it. Now, I'm in the debugger. I've just edited some code. This is this late binding thing. The code hasn't finished executing yet. So now I can carry on executing with my new method, and now it works. So I've actually interrupted the code, written some new code, and kept going all at the same time. And it's actually really common in Smalltalk to write code in the debugger. You basically write a method, it doesn't work, you just type it in until it does work. Go to the next thing where it doesn't work, and you keep typing. So you literally can code in the debugger. You don't, because there's no files. It's like, which file did I have to put this in? I don't know, I don't care. It's not a file-based system. I didn't have to define, a new file for this particular method or anything. If I want to create a new thing, let's say I have an animal. If I want to create a new animal, in a object-oriented language, you might say something like this, right? There's no constructors in Smalltalk. How do you make a new object in Smalltalk? You send a method. You send a message. So I have to send a message. Animal is a thing. It's a class. I send it a message. If I want a new animal, I say cat. And now it says I'm a cat. Right? So everything is an object. So classes are objects. So if I say 42, what is your class? It says I'm a small integer. Okay. Now, in C# and Java, classes are not the same thing. Then there's no. You have things like static methods. There's no static methods in Smalltalk. Everything is an object. So the class is an object, and you can talk to the class. You can say, "Hello, class. What is your class?" It says, "I'm the class of small integer." So that's the kind of static, the method, the parent class of small integer. Okay, hello, small integer class. What is your class? I'm class metaclass. Hello, metaclass. What is your class? I'm metaclass class, and so on and so forth. And actually, at that point, you get interlude. The class of metaclass is class again. But the thing is that everything is an object, and I can just browse it. There's a browser everywhere. I can go straight to a particular browser. I'm now browsing metaclass. If I go to 42 class here and I browse it, and I'm looking at small integer, which is a subclass of integer, which is a subclass of float, which is a subclass of arithmetic value, and so on. Here's all the methods down here. So this is a full IDE. And at any point, there's no, this is the source code. There's no text file, so I can just change this code right now and save it, and I don't have to worry about this. All this stuff gets in the way. The whole thing of text files, that's nothing to do with programming. That's just overhead. If I want to do programming, I just type some stuff and it works. That's programming. Okay, so if you want object-oriented programming. Now, here's another question for you. Let's go to the animal class. Now, let's say I don't like animal. I want to create a new kind of animal. How do I create a new kind of animal? Do I create a class definition somewhere? No. I send a message to somebody. Everything is sending a message. Who do I send a message to? I send a message to object. So this actually is a message. It's a message with 5 different parameters. So this is the name of the subclass. This is what the instant variables are, the class variables, and so on. If I send a message to object and I say, actually, I want to send this message, subclass animal 2. Okay, and I'm going to do it. And all of a sudden, there it is. I've got a new, let's say that. I've got a new class right there. And if I want to add a new instance variable, I just send the same message again. No, let me just, there you go. So now I've got a name and an age. So everything is sending messages. Like I say, everything is an object. There's nothing which is not an object. The compiler is an object. The stack trace is an object. The entire thing is an object. And if I do, the debugger is an object. Everything is an object. Really, really is object-oriented in the most literal sense. One final thing is let's look at if true and if false. I said there were no control statements. So how do I do if true or false if there's no control statements in the language? Well, I send it a message, of course. That's the right answer to everything. So let's say 1 equals 1, that's going to be true. And I send it a message, and I say if true, if false. And like this. So these things, this is a message with 2 parameters. That's the first parameter. There's the first part of the message. There's the second part of the message. And these parameters are blocks. You can think of them almost like lambdas in other languages. It's basically a thing to run. So if I do that, it says yes. And if I say is 2 equal to 1, and I say no. Now let's look up the implementation of if true, if false. And it turns out there are 3 implementations of it. By the way, notice that I don't have to worry about, you talk about browsing source files and stuff and finding things in an IDE. Smalltalk's had this, again, since the 80s. You just go straight to the definition, straight to the references. So there are three definitions. One is for Boolean, and the Boolean definition says, subclass responsibility, meaning I don't care, not my problem. Then the way Smalltalk works is there's a class called true, and there's a class called false. And they are separate classes. So the false class, it implements this. How does it implement it? It just takes the false part, the lambda that's sort of passed in, the block that's passed in, and it just runs it. And if you go to the implementation of true, it just takes the true thing that's passed in and runs it. So it's just a message. Like I say, there is no true, false statement. Everything is done through messages. So that's just why the syntax is so minimal, literally only 3 keywords. And everything, if you have a very, very powerful concept, and you really take it to the max, you can do incredible things. Right, that is enough small talk. Let me go back to my presentation. Okay, so what can we learn from Smalltalk? A really, really consistent model. Everything is an object, everything is a message. That's it. Once you understand that everything's an object and everything's a message, you understand everything about Smalltalk. Really, that's it. Very, very minimal syntax, making a powerful language. So rather than hacking around with special edge cases, like we need this or we need this, like, no. You design it so you can do anything in the language. And be awesome. The people, this is not a joke. The people who designed Smalltalk were trying to make it awesome, and they were trying to make people fall in love with it. They spent a lot of time on this kind of stuff. Same thing like the early people who did the Mac. They spent a lot of time making cute icons and stuff. They really, really cared about the user experience, which is why people did fall in love with Smalltalk, and people did fall in love with the Mac. It's really important, this kind of stuff. Making people fall in love with you is actually a very important goal. All right, so Smalltalk is, a lot of people say, well, Smalltalk was cool. It's kind of a dead end, this whole kind of interactive thing, no text files, it's interactive, it's self-contained, it doesn't talk to the outside. Well, what kind of, that's really a dead end for programming languages. So let's talk about language X, which squeaked in 1979. So in the 1980s, people would literally pay thousands of dollars to use this language, all right? Literally thousands of dollars. And the descendants of this language have been incredibly popular. They're really at the heart of the dominant software products. Okay, any ideas what I'm talking about? And its grandchild, I would say, is the most popular programming language in the world. Yes, the answer is, what language am I talking about? I'm talking about VisiCalc. Okay, VisiCalc basically drove the PC industry. People would spend $5,000 to buy an Apple II so they could run VisiCalc. And then VisiCalc begat Lotus 1-3, which is the most popular software of the 80s. And then Lotus 1-3 begat Excel, which is the most popular software of the 90s and the 2000s. So this is really incredibly powerful, okay? And what is so important about VisiCalc is it's got a consistent model, okay? It's a programming language. It's not just an application, it's a programming language. It's got a consistent model like Smalltalk. It's got a highly interactive environment, and it's got a programming language, and they all fit together really nicely. Now, if you took away the programming language, it wouldn't work. The whole thing is you can program formulas. They're little tiny formulas, but they're still formulas. It's a programming language. It's a very domain-specific programming language. It's all about one thing. How do you work with a spreadsheet? It's expression-based, okay? Everything returns, every formula returns a new thing. It doesn't set variables. And it's something that non-programmers can understand. They can all understand A1 plus B2, okay? Anyone could write that. It's functional. You can do these things like sum all the numbers from this to this. There's these functions built in. And you program by filling in slots. You don't think you're programming. You're filling in this formula here and this formula here. There's no text files. You don't have to write this text file. You basically fill in all the slots. And it's like Prolog. They magically kind of unify. It's like you put this one here, and this one gets filled in automatically. So there's a lot of things that VisiCalc kind of took from these other previous languages, which is really very useful. So what can we learn from VisiCalc? Programming is not just writing text files in a C-like language. There's more to programming than that. Programming is getting a computer to do what you want. And Excel is a classic example. There's more people using Excel than writing any kind of regular programming language. So it's not just for programmers. People love to interact and explore, okay? This whole thing of making people wait, making people compile, it's like interactivity is a really fantastic way. And programming for a specific domain is actually much more important than for general purpose programming. Okay, you know, Excel isn't. You're trying to write. If you tried to do Excel kind of stuff in a general purpose language, it would be horrible. The very fact is, it's very specifically designed for that one particular purpose, and that's what's making it great. So use the right tool for the job. Don't use a hammer. You know, or you do use a hammer if it's the right tool for the job, but don't always use a hammer for everything. So there are many different approaches to solving problems. It's a good idea to have a big toolbox, okay? Don't just think, I know C#, I know Java, I know JavaScript. Go and learn APL, go and learn Prolog, go learn something. It'll help your mind expand. And also, please, C-style syntax is not the only syntax in the world. I hear people say, I can't read a language that doesn't have curly braces. It's like, all these languages, none of these languages had curly braces. They all had, by the way, they all had periods at the end of a sentence, like proper grammar, okay? Smalltalk uses periods, Prolog uses periods. This whole thing of using semicolons to end a sentence, your English teacher would be very upset with you. No curly braces anywhere, and no dot syntax. So Smalltalk, the object in our language, doesn't have dot syntax. Okay, it has messages. So going back to this quote, a language that doesn't affect the way you think about programming is not worth knowing. So go forth and expand your galaxy brain. Go and learn some new languages and have fun. All right, thanks very much. And I will put the slides on my website on 4 from 40. And there's more functional programming in this room with the rest of the conference. So have fun. Thanks very much.